Picture a fully loaded 18-wheeler cruising down the highway at sunset. It's a common sight, but there is an incredible amount of physics happening right where the rubber meets the road. We're talking about a gross vehicle weight of up to 80,000 pounds. When that much mass hits a pothole or a rough patch at 70 miles per hour, it creates massive physical shockwaves. This animated diagram shows how all that weight and kinetic energy travels down from the cargo box, through the heavy steel chassis, and concentrates entirely into the small center points of the wheels. All of that crushing force converges on a dense mechanical space barely larger than a dinner plate. Engineers call this the wheel end, the critical bridge connecting the truck's axle to the wheel itself. If this small hidden assembly breaks under the pressure, the truck loses its wheel instantly. Designing a part that can survive these extremes without failing is one of the toughest challenges in mechanical engineering. To understand how it works, we start with a bare metal axle shaft. This is the solid foundation of the truck's suspension. Over that shaft goes the hub, a heavy, forged steel shell that the wheel bolts onto. But you can't simply slide a bare metal hub over a bare metal shaft. Under 80,000 pounds of pressure, the friction would grind the parts to dust in minutes. To solve this, engineers use a clever set of rollers called tapered roller bearings. This diagram shows tapered bearings sliding into the hub. Their specific angles smoothly carries the crushing downward weight while absorbing harsh side-to-side cornering forces. These bearings must be locked in with exact millimeter spacing. If slightly loose or tight, the wheel will wobble. Every lane change creates severe twisting forces. By locking these angled rollers tightly into the correct spacing, the assembly smoothly absorbs the twist, keeping the heavy wheels firmly attached to the truck. While the bearings handle the physical weight, highway speeds create a rapid, invisible threat, friction. This 3D model shows what happens when you combine the friction of spinning metal with the intense heat of applying the truck's heavy brakes. The heat spreads through the metal chamber, sending temperatures skyrocketing. When metal gets hot, it expands. That thermal expansion threatens to warp the components and ruin the exact delicate bearing spacing we just set up. To prevent a meltdown, the entire chamber is flooded with industrial oil or heavy grease. The fluid constantly surges over the spinning rollers. It absorbs the heat and provides a slippery cushion that keeps the rotation smooth. By trapping this fluid inside to constantly cool the metal, a heavily loaded truck can safely brake repeatedly without melting its own structural joints. We now have a perfectly cooled, oiled interior, but the outside world is filled with freezing rain, gritty mud, and road salt constantly blasting against the spinning metal. If one drop of dirty water or a stray grain of sand breaches that outer shell, it will act like sandpaper and quickly destroy the bearings. The defense against this is a specialized barrier called a multi-lip cassette seal. Looking at a microscopic cross-section in this diagram, we can see exactly how it works. The inner rubber lips act like a vault door, trapping the essential oil inside. Meanwhile, the outer lips sweep away incoming dirt and water. The lifespan of the massive wheel end actually comes down to this tiny piece of rubber. By keeping the clean oil in and the messy world out, the truck can stay on the road for over 1,000,000 miles. Our mechanical fortress is almost complete. To work with a modern truck, it just needs one final digital component. Engineers plug a small computerized sensor into the hub. This is part of the anti-lock braking system, or ABS. Think of it like a highly precise, smart speedometer specifically for that single wheel. This diagram shows the sensor in action. It continuously reads the hub's rotation and pulses real-time data back to the truck's main computer, helping to prevent the truck from skidding during sudden stops. Add the heavy-duty steel studs, tighten down the lug nuts, mount the massive tire, and the fully assembled wheel end is ready to hit highway speeds. Making these components out of lighter alloys could save fuel, and using simpler seals would lower costs. But because a mechanical failure here would be catastrophic, every design choice prioritizes long-term durability over weight or price. So the next time you see an 18-wheeler out on the highway, you have the X-ray vision to see the reality, a carefully balanced system of steel, oil, and rubber holding 80,000 pounds in place